There's a class of matrices where finding the inverse is free. You just flip rows and columns. Here's a 3 by 3 matrix Q. Its first row is 0, 0, 1, its second row is 1, 0, 0, and its third row is 0, 1, 0. Now transpose it, swap rows and columns. Q transpose has first row 0, 1, 0, second row 0, 0, 1, and third row 1, 0, 0. Now multiply Q transpose times Q. Work through the entries, and the 3 by 3 identity matrix appears. Every diagonal entry is 1, and every off-diagonal entry is 0. No Gaussian elimination, no determinant formula, no cofactors, just the transpose. Q transpose equals Q inverse. The secret is hiding in the columns of Q. To understand why, we need to unpack two properties those columns share. Two vectors are orthogonal when they're perpendicular, meeting at a 90-degree angle. Algebraically, their dot product equals 0. Here are two vectors in the plane. Q1 equals the vector 1, 0, and Q2 equals the vector 0, 1. Q1 dot Q2 equals 1 times 0 plus 0 times 1, which equals 0. They are perpendicular, but orthogonal alone isn't enough. We also need each vector normalized, scaled to unit length. A vector has unit length when its dot product with itself equals 1. Q1 dot Q1 equals 1 squared plus 0 squared, which equals 1. Q2 dot Q2 equals 0 squared plus 1 squared, which equals 1. Both vectors sit on the unit circle. When vectors are both orthogonal and normalized, we call them orthonormal. The formal conditions are qi transpose qj equals 0 when I does not equal j, and qi transpose qi equals 1. Now let's pack orthonormal vectors as columns of a matrix Q. Take Q1 equals cosine theta, sine theta, and Q2 equals negative sin theta, cosine theta. Form Q with Q1 as column 1 and Q2 as column 2. So Q is the 2 by 2 matrix with cosine theta and sine theta in the first column, and negative sine theta and cosine theta in the second column. Q transpose has Q1 transpose as row 1 and Q2 transpose as row 2. That gives us cosine theta and sine theta in the first row, and negative sine theta and cosine theta in the second row. Now let's multiply Q transpose times Q. Each entry in row I, column j equals the dot product qi transpose times qj. Entry 1, 1, Q1 transpose times Q1 equals cosine squared theta plus sine squared theta, which equals 1. Entry 1, 2, Q1 transpose times Q2 equals cosine theta times negative sine theta plus sine theta times cosine theta. That's negative cosine theta, sin theta plus cosine theta, sin theta, which equals 0. Entry 2, 1, Q2 transpose times Q1 gives the same calculation, also 0. Entry 2, 2, Q2 transpose times Q2 equals sine squared theta plus cosine squared theta, which equals 1. The result is the 2 by 2 identity matrix. Q transpose Q equals I. Here's the algebraic payoff. Suppose Q is a square matrix and Q transpose times Q equals the identity. Then Q transpose equals Q inverse. Why is this true? Well, Q transpose times Q equals, means that Q transpose is the left inverse of Q. And for square matrices, a left inverse is automatically a two-sided inverse. So Q times Q transpose also equals I. Therefore, Q transpose is the full inverse of Q. A square matrix with orthonormal columns is called an orthogonal matrix. Notice the naming quirk. The matrix is called orthogonal, but the columns must actually be orthonormal, meaning perpendicular and of unit length. Being merely orthogonal is not sufficient. One more key fact, orthonormal vectors are always linearly independent. Perpendicular directions can never combine to produce the zero vector. So n orthonormal vectors in Rn form a basis, and Q is guaranteed to be invertible. Its inverse is simply the transpose. No raw reduction, no cofactors, No determinant computation needed. Now let's see this in action with 4 concrete examples. Example 1, a permutation matrix. Take Q with columns E2, E3, E1, the standard basis vectors, just rearranged, written out. Q equals the matrix. Row 1 is 0, 0, 1. Row 2 is 1, 0, 0. Row 3 is 0, 1, 0. Let's identify each column. Column 1 is E2, which is 0, 1, 0 transpose, shown in blue. Column 2 is E3, which is 0, 0, 1 transpose, shown in orange. Column 3 is E1, which is 1, 0, 0 transpose, shown in green. Now let's check orthonormality. Each column is a standard basis vector, so each has exactly one entry equal to 1, and the rest 0. That means each column has length 1. Next, the dot product checks. No two columns share a non-zero entry in the same row position, so all pairwise dot products equal 0. Also, normal columns confirmed. Now let's compute Q transpose. We flip rows to columns, giving row 1 is 0, 1, 0, row 2 is 0, 0, 1, row 3 is 1, 0, 0. Finally, multiply Q transpose times Q. Every diagonal entry comes out to 1, and every off-diagonal entry comes out to 0. So Q transpose Q equals the 3 by 3 identity matrix. Notice that the transpose simply undoes the permutation. It sends the rearranged basis vectors back to their original positions. Example 2, the rotation matrix. Q has first row cosine theta, negative sin theta, and second row sin theta, cosine theta. The columns of Q give us our two vectors. Column 1 is Q1, equal to cosine theta, sin theta. Column 2 is Q2, equal to negative sin theta, cosine theta. Now let's verify orthonormality. First, the length of Q1 squared, cosine squared theta, plus sin squared theta. By the Pythagorean identity, this equals 1. Next, the length of Q2 squared, negative sin theta, squared plus cosine squared theta, which is sin squared theta plus cosine squared theta, also equal to 1. Now for the dot product of Q1 and Q2, cosine theta times negative sin theta plus sin theta times cosine theta, that gives us negative cosine theta sin theta plus cosine theta sin theta, which cancels perfectly to give 0. Also normal columns confirmed. Now for the geometric picture. On the unit circle, Q1 points at angle theta from the horizontal axis, and Q2 is perpendicular to it, rotated 90 degrees further. Geometrically, multiplying a vector by Q rotates it by angle theta. Multiplying by Q transpose rotates by negative theta, undoing the rotation. And that's exactly what the inverse does. So Q transpose equals Q inverse, and we can see this both algebraically and geometrically. Example 3, Hadamard matrices. The 2 by 2 Hadamard matrix is 1 over the square root of 2 times the matrix with entries 1, 1 in the first row, and 1, negative 1 in the second row. Let's extract the columns. Column 1 is 1 over the square root of 2 times the vector 1, 1. Column 2 is 1 over the square root of 2 times the vector 1, negative 1. Now let's verify these columns are also normal. For each column's squared length, we compute 1/2 times 1 squared plus 1/2 times 1 squared, which gives 1/2 plus 1/2 equaling 1. So both columns are unit vectors. For the dot product of column 1 and the column 2, we get 1/2 times 1 plus 1/2 times negative 1, which equals 1/2 minus 1/2, equaling 0. So the columns are orthogonal. Since the columns are both unit length and orthogonal, this matrix is also normal. Now for the 4x4 version, it uses a block construction, place H on top, and H, negative H on the bottom, where H is the 2 by 2 matrix of plus and minus 1s. Then scale everything by 1/2, since 1/2 equals 1 over the square root of 4. This produces a 4x4 grid of +1 and -1 entries, color-coded blue and red. An interesting side note, whether a Hadamard matrix exists for every size divisible by 4 remains an open problem in mathematics. Example 4, a rectangular matrix. Let Q equal 1/3 times the matrix with rows 1, -2, 2, -1, 2, 2. This is a 3x2 matrix. It has 3 rows and 2 columns, so it is not square. Let's check whether its columns are also normal. Column 1 is Q1 equal to 1/3 times the vector 1, 2, 2. Its length squared is 1/9 times the quantity 1 plus 4 plus 4, which equals 9/9, which equals 1. Great, so column 1 is a unit vector. Column 2 is Q2 equal to 1/3 times the vector -2, -1, 2. Its length squared is 1/9 times the quantity 4 plus 1 plus 4, which also equals 9/9 equals 1. So column 2 is also a unit vector. Now let's check orthogonality. The dot product of the two columns is 1/9 times the quantity -2 minus 2 plus 4, which equals 0. So the columns are also normal. Now Q transpose Q is a 2x2 matrix and it equals the 2x2 identity. However, Q times Q transpose gives a 3x3 matrix, and this is not the 3x3 identity. Without a square matrix, Q transpose is only a left inverse. It is not a full inverse. The key takeaway, the term orthogonal matrix applies only to the square case. A rectangular matrix with orthonormal columns has Q transpose Q equal to the identity, but QQ transpose does not equal the identity. Permutations, rotations, Hadamard matrices, these all share a deep geometric truth. Orthogonal matrices preserve lengths and angles. Multiplying by Q doesn't stretch or compress. It only rotates and possibly reflects. This is why orthogonal matrices appear everywhere in mathematics and its applications. Let's summarize what we've seen in a comparison table. First, permutation matrices. Their structure consists of rearranged identity columns. They are also normal because the columns are standard basis vectors, which are already unit length and perpendicular. Permutation matrices appear in combinatorics and graph theory. Second, rotation matrices. Their structure is the 2x2 matrix with cosine theta and negative sin theta in the first column and sin theta and cosine theta in the second column. They are also normal because of the Pythagorean identity cosine squared theta plus sin squared theta equals 1. Rotation matrices appear in computer graphics and physics. Third, Hadamard matrices. The structure consists of +1 and -1 entries scaled by 1 over the square root of n. They are also normal because of their balanced pattern of +1s and -1s. Hadamard matrices appear in signal processing and coding theory. Beyond these, QR factorization uses orthogonal matrices in numerical linear algebra. Principal component analysis in data science relies on orthogonal transformations, and Fourier matrices drive signal processing. In every one of these applications, the free inverse, Q transpose equals Q inverse, makes computation dramatically cheaper, no elimination, no cofactors, no determinant computation needed, just a transpose. Here is the core principle to remember. Whenever you find perpendicular unit vectors, stack them as columns. You are one transpose away from an inverse.